So hello everyone, I'm Norman Wahlberger. We're here at the University of New South Wales, and we're carrying on with our History of Mathematics series here. Today's lecture is going to be on hypercomplex numbers, which is an interesting chapter of algebra that developed in the 19th century. And there's a number of interesting individuals that contributed to it. So let's talk a little bit about arithmetic. So there are various arenas for doing arithmetic. And historically, we certainly know about the rational numbers. Often denoted Q, or maybe type RAT. And we have decimal numbers, which are often called real numbers, although I myself have some problems with the foundational aspects of real numbers. And there are then complex numbers, usually denoted C, where we're talking about things of the form A plus BI. And the main aspects of this arithmetic is that we have these operations. The arithmetic really starts with addition and then multiplication. These are the primary arithmetical operations. And the secondary ones of subtraction and division. And okay, these days we recognize that there are certain laws that are satisfied in these kinds of situations when we're dealing with these kinds of arithmetic. And these laws of arithmetic are now well studied and presented to students in primary school. And so they learn about the commutative laws. Commutative laws are, well, there's one for addition, A plus B equals B plus A. There's also one for multiplication, A times B equals B times A. Then there's the associative laws. Where we have three things, so A plus B plus C. If we have three numbers, A, B, and C, and we add B and C first and then add A to that, well, that's the same as what we get when we add A and B first together and then add C. And there's a multiplicative version of that. Just A times B times C equals A times B times C. And then there's the distributive laws. That connect addition and multiplication. So A times B plus C equals A times B plus A times C. Or I suppose we could do it the other way around. A plus B times C equals A times C plus B times C. Now this kind of description of arithmetic in terms of operations and then analyzing, what kind of laws were satisfied by those operations became really only clear in the 19th century. In fact, the embracing concept here that includes all of these is the notion of a field. So this is a mathematical concept of a field, which was introduced in 1871 by Richard Dedekind. Although it actually has its origins perhaps in the work of Galois, some 40 years before, so more indirectly by Galois around 1830. We're going to talk more about Galois and his contributions with respect to polynomial equations later on. Okay, so what is a field? Well, a field is a little bit technical, but it's basically an arena for doing arithmetic where you have an addition, you have a multiplication, and you have these three laws satisfied, as well as a few others. And the few others concern special numbers like 0 and 1 and minus 1. We want 0 and 1 and minus 1 to behave the way they do normally when we're doing arithmetic with rational numbers. Okay. So there's a few more aspects of the definition of the field which I'm not going to mention. Okay, so earlier, this third example of complex numbers, of course, historically has sort of an ambiguous aspect because people struggled with understanding what complex numbers were. Okay? And they eventually realized that there was a geometrical aspect to complex numbers. So the geometrical aspect of complex numbers was developed by Argand and Gauss. And there was this realization that we could visualize complex numbers in terms of points on a plane, where we think of a 1 as being on this horizontal axis, so this is like the usual number line, and then we have a kind of an imaginary number line consisting of multiples of I in that direction. And then if we have a typical complex number, say a plus bi, well, it means that its components are a and b in that direction there. And we sometimes represent such a complex number by an arrow from the origin. Now, it turns out that the multiplication of complex numbers and the addition of complex numbers are intimately connected somehow with the geometry of the plane. And in particular, these complex numbers were understood to explain rotations and dilations. So rotations and dilations of the plane are naturally linked to multiplication of complex numbers. So let me just explain why that is here in this picture here. So here's a particular complex number, z, which you can see is, has a certain angle from the x axis, maybe an angle of theta there, and it has a certain distance or length from the origin, which is maybe around 2 or maybe a little bit more than 2, something like that. And in terms of, if you look at what happens when you multiply by z, well, this multiplication by z has a geometrical aspect which is intimately connected with this angle or angular separation and the length of this vector itself. So if you take an arbitrary point w and you multiply by z, what happens to it? Well, so if you think in terms of vectors, if that's w, then when you multiply by z, what you're going to get is you're going to get something that's moved over by another angle, theta, the same theta that appears there. So if we sort of add theta to the w, then we know that wz is going to lie somewhere in that ray. And how far on that ray? Well, it's going to stretch w by a factor, and the factor is exactly the length of this thing here. So this length is a little bit more than 2. It means that when we multiply by z, w is going to be sent to something else, say up here, which is roughly 2 times the length of w. All right. So in this way, multiplication by this complex number z in the plane is affecting both a rotation and a dilation at the same time. And this gives us a very convenient way of thinking about rotations and dilations. It gives us a very effective sort of algebra or arithmetic with these transformations of the plane. Okay, so this was sort of understood by the 1830s. People understood this very clearly. And some people started thinking, well, okay, can we do something like this in higher dimensions? Can we start to understand rotations in a higher dimensional space or dilations in higher dimensional space in terms of some more complicated arithmetic? Is there an arithmetic of points in three-dimensional space? Right, the complex numbers are giving us an arithmetic in two-dimensional space. So a natural question is there an arithmetic in three-dimensional space? Can you add and multiply vectors in three-dimensional space? And this kind of question, well, a number of people started thinking about this issue. Okay, so there are a number of people, many mathematicians, then started to investigate higher dimensional arithmetic, we might say. Higher dimensional arithmetic, whatever that might be. And we're talking about people like Hermann Grassmann and Clifford and Hamilton, his friend Graves, Cayley, De Morgan, Peacock. And the person we're going to talk about most today is William Rowan Hamilton, who plays a very important role in this story. He was an Irish mathematician. His dates were from 1805 to 1865, and he was a prodigy, a mathematical prodigy. In fact, he was a very intelligent fellow even at an early age, where he mastered a lot of classical languages. He was also a calculating prodigy. So this is, of course, before the age of computers or calculators, and people who had arithmetic skills, who could do arithmetic in their heads, were somehow sort of notorious and almost famous. And there were quite a few prominent young, usually men, who had these extraordinary abilities to do vastly large arithmetic problems in their heads. And they would go on tour, sort of like Katy Perry today or something, but you know, you go around showing off your calculating skills. And Hamilton was in this class, but he was outdone by a fellow called Zara Colburn, I think, who was an American, for example, who could calculate the number of minutes in 1811 years in just half a minute or something like this, or multiply two 10-digit numbers in their heads or things like this, and so he had this prodigal aspect when he was young, and then he ended up going to Trinity College in Dublin in 1823 when he was still relatively young, and then became Ireland's most famous and respected scientist, mathematician, and a physicist as well. So he made important contributions in mathematical physics, in optics, in reformulating Newtonian Lagrangian dynamics, something called Hamiltonian dynamics. Which were to play a very important role in 20th century developments in physics. But we're mostly interested in his passion in his discovery of quaternions. Okay. So he discovered these things called quaternions, which ended up being examples of these hypercomplex numbers. And they really are the first example of an arithmetic that goes beyond complex numbers. And in fact, there was then this interesting, very interesting conflict between the quaternions that Hamilton introduced and the vector analysis of Gibbs and Heaviside. I'll talk a little bit more about that a little bit later. Okay, so to understand these quaternions, which is what we want to do now, we have to go back to the complex numbers and talk about the most important property of complex numbers. All right, so the most important property of complex numbers is surprisingly not even stated properly in most texts. Okay. It's the following. If you have a complex number z equals a plus bi, then associated to that is a size or a number that encodes how big it is. And that number we're going to call q of z. And it's by definition z times z bar. Okay. So z bar is the complex conjugate of a plus bi. So this is a plus bi times the complex conjugate is a minus bi. It's what you get when you negate the imaginary component of the complex number. Okay, this is then a difference of squares, and you just multiply it out using the fact that I squared is equal to minus 1, and you get a squared plus b squared. Okay. So we're going to call this the quadrants of z. It's not usual terminology. It's terminology that comes from rational trigonometry, but it makes a lot of sense. Often this is called the length squared, but it's better to think of the length as being the square root of the quadrants. Okay? So the length of z is actually, the definition is it's the square root of the quadrants of z. So if you want to calculate the length, first you actually calculate the quadrants and then you take its square root. But of course the square root is a highly problematic operation if you want to do things exactly, because the operation is really only an approximate operation. You can't actually calculate the square root of most numbers. Requires an infinite amount of decimals, an infinite amount of computation. So my point of view is this is actually the fundamental concept that students really ought to be taught before they are taught the length. Okay, so now what is the most important property? Here it is right here, that if you take two complex numbers, z1 and z2, and you compute the quadrants of the product, it's the product of the quadrances. All right, this is the most important property of complex numbers. And in terms of length, we can sort of rewrite it if we want to as saying that the length of z1 times z2 is the length of z1 times the length of z2. And you'll recognize that's really the property that I've already talked about when I was talking about multiplying by z, saying that when you multiply by z, then let's say you're multiplying by z2, then the length of z1 gets multiplied by the length of z2. Okay, so why is this property true? Well, we can think about it in terms of an algebraic relation. So if z1 is, say, a1 plus b, or say I'll put the I there, ib1, and z2 equals a2 plus ib2, then Z1 times Z2, I remind you, is the imaginary part, the real part is A1, A2 minus B1, B2. I might put brackets around there. And then the imaginary part is A1, B2 minus A2, B1. And so this statement really comes down to the following identity. Okay. The quadrants of Z1, Z2 is the sum of the squares of the entries. So we're saying that A1, A2 minus B1, B2 squared plus, and then the imaginary part is A1, B2 minus A2, B1 squared. That's the quadrants of Z1 times Z2. And that's, according to the formula, the quadrants of Z1 times the quadrants of Z2. Namely, A1 squared plus B1 squared times A2 squared plus B2 squared.
For the imaginary part, isn't it A1, B2 plus A2, B2?
It is. Oh, thank you very much. Excellent. Okay, so of course, yes, the imaginary part is A1, B2 plus A2, B1. So I should put a plus sign here. Thanks very much. Okay, now that we've got that correct, now we can say, well, is this true? And this is a true identity. If you expand out the left-hand side and you expand out the right-hand side, then they agree. They're exactly the same. In fact, this identity goes back to Diophantus. Who was an ancient Greek mathematician in the later part of the Greek period, around 300 AD. Although he sort of used it indirectly, it was perhaps explicitly written down first by a fellow called Leonardo of Pisa. Leonardo of Pisa, also known as Fibonacci. The same Fibonacci who gave us the Fibonacci sequence around the 1200s. Okay, so this is a very interesting identity, and so let's see, why was Diophantus interested in this identity? All right, so this identity that we've just written down, here it is again. A1, A2 minus B1, B2 squared plus A1, B2 plus A2, B1 squared equals A1 squared plus B1 squared times A2 squared plus B2 squared. It has a kind of a twin variant. So a variant of that is A1, A2 plus B1, B2 all squared plus A1, B2 minus A2, B1 squared. This minus now in the right spot, equals A1 squared plus B1 squared times A2 squared plus B2 squared. So that's obtained by just replacing B1 with minus B1 in the previous one. So this formula, well, these formulas were also known and talked about to Al-Khazin in 950, who was commenting on a problem of Diophantus. So Diophantus wrote a book where he dealt with a number of arithmetical problems. And one of them was the following, is to find a rule for finding a hypotenuse of a right triangle which is the product of hypotenuses of two given ones. So for example, if we have a triangle, say with sides 3 and 2, then the ancient Greeks thought about the areas on the three sides. Pythagoras' theorem had as we've talked about before, had an interpretation in terms of areas. So if this is length 3, then this area will be 9, and this area will be 4, and so this area here is 13. Okay. And let's say we have another triangle whose sides are 2 and 1, then similarly the area on the hypotenuse there is 5. And so suppose we're interested in finding another triangle whose hypotenuse area is the product of these ones. That was Diophantus' problem. So 13 times 5 is 65. So the question is, what sides do you have to put there in order that you can cook up a right triangle whose the square built on this side, or the quadrants of this side, is the product of the quadrants here. And that's really asking the question, can we write 65 as x squared plus y squared? How do you do that where x and y are integers? How do you write 65 as a sum of two squares? Well, a little bit of experimentation shows that if you put that equal to 7 and that equal to 4, then that will work, because 65 is equal to 49 plus 16. So that's how you can write 65 as a sum of two squares. And Diophantus was tackling this kind of problem, and basically Al-Khazin noted that what's really involved is this kind of identity. Much later, the great 17th century French mathematician Fermat, who was responsible for invigorating number theory in the sort of modern European era, asked which numbers can be written as a sum of two squares. So for example, 13 can. 13 is 3 squared plus 2 squared. And 5 can. 5 is equal to 2 squared plus 1 squared. But 15 if you try to write 15 as the sum of two squares, you find out that it doesn't work. So 5 can be represented as a sum of two squares, 13 can, but 15 can't, for example. So it's a little bit subtle, and Fermat was interested in this question. And one thing that he realized was the following theorem, that if Q1 and Q2 are sums of two squares, then so is Q1 times Q2. Right? And here's the proof is exactly contained here, or in the Diophantus identity, same thing. So if you have your number Q1, which is written as a sum of squares, and you have Q2 written as a sum of squares, and you're interested in writing the product as a sum of squares, then you have to use this particular combination. If you use this and this, then this squared plus this squared will be equal to the product. So this identity is exactly solving this question and is the proof of this theorem. So if you know that you have two numbers, both of which are sums of two squares, then the product is also a sum of two squares. Well, considerably later, the 18th century mathematicians interested in the question of, okay, not every number can be written as a sum of two squares. Can every number be written as a sum of three squares? Well, it turns out that the answer is no. Not every number can be written as a sum of three squares. How about four squares? Well, Euler realized that, or he certainly knew that it was true, but he didn't have entire proof. Euler knew that four squares suffice, that every number can be written as a sum of four squares. And one of his key ideas is that in 1748 he proved that the product of two numbers which are sums of four squares is also the sum of four squares. So that was the great Euler who proved that, and then we're going to talk about that in a second. But that was then a critical, played a critical role in the subsequent proof by Lagrange, who established what Euler knew but couldn't quite prove. Euler and Lagrange then the fact that theorem that every number, every natural number, can be written as a sum of four squares. That's a great little exercise if you're on the bus. Just pick yourself a number, 37. How do you write 37 as a sum of four squares? Well, that one's easy because it's 6 squared plus 1 squared plus 0 squared plus 0 squared. 0 is allowed. That's too easy. What about 35? How do we write 35 as a sum of four squares? 5 squared plus 3 squared plus 1 squared plus 0 squared. And the theorem is that every number, no matter how big it is, can be written as a sum of four squares. Okay, so underlying this is this theorem of Euler, which was an extension of the identity of Diophantus. Okay? And this extension is pretty interesting and plays a very interesting role in the development of quaternions, even though Hamilton was in fact unawares of it. So here is the identity of Euler. Okay, I'll write it like this. A squared plus B squared plus C squared plus D squared times alpha squared plus beta squared plus gamma squared plus delta squared equals A times alpha minus B times beta minus C times gamma minus D times delta all squared plus alpha A beta plus B alpha plus C delta minus D gamma squared plus A gamma minus B delta plus C alpha plus D beta squared plus A delta plus B gamma minus C beta plus D alpha squared. So this is an identity in the sense that if you expand out the left-hand side and you expand out the right-hand side and simplify, you see that they're both exactly the same. So this is true for all numbers A, B, C, D, and alpha, beta, gamma, and delta. And it's some kind of four-dimensional analog of the Diophantous identity that's responsible for the quadrant's multiplicative property of complex numbers. Okay, so now we move forward to Hamilton and his friend Graves. So Hamilton was unaware of Euler's formula. In fact, Hamilton didn't have a very good idea of the number theory that's naturally connected with this question. But he was interested in how do you multiply three-dimensional vectors? How do you multiply three-dimensional vectors? So just the same way as we multiply, or how to do arithmetic with three-dimensional vectors really is the question, but in particular how to multiply three-dimensional vectors, which in a way that mimics what goes on with complex numbers as two-dimensional vectors. And he worked on this problem for many years, like a dozen years. He struggled with the idea of trying to make a sensible multiplication where you got an arithmetic that satisfied the usual commutative, associative, distributive laws. And he wrestled with things and so on and so forth. And it took a long time for him to realize that such a thing doesn't actually exist. All right. And I want to quote something that he wrote to his son later on about this period. It's quite interesting. So eventually he was, in 1843, he was walking along a bridge. So he wrote to his son, he said the following: "But on the 16th day of the month, namely October 1843, which happened to be a Monday and a council day of the Royal Irish Academy, I was walking along to preside," because he was the president, "and your mother was walking with me along the Royal Canal. And although she talked with me now and then, yet an undercurrent of thought was going on in my mind, which gave at last a result. An electric current seemed to close, and a spark flashed forth, the herald, as I foresaw immediately, of many long years to come of definitely directed thought and work. I pulled out on the spot a pocketbook, which still exists, and made an entry there and then. Nor could I resist the impulse, unphilosophical as it may have been, to cut with a knife on a stone of Brougham Bridge the fundamental formula with the symbols I, J, and K." So he took out his pocket knife and he wrote down the following equation: I squared equals J squared equals K squared equals I, J, K equals -1. He wrote that down on his bridge, which contains the solution of the problem. But of course, as an inscription, it has long since moldered away. So he wrote that 20 years later about his discovery. And this is basically the day where he discovered quaternions, which are a four-dimensional version of complex numbers. So he realized at some point that his long search for three-dimensional multiplication was fruitless, but if you go to 4 dimensions, there is something there, and it's something very beautiful. Okay? And these are the things called quaternions, and they form some higher dimensional analog of complex numbers. Okay, so what are these quaternions? Well, they're basically what you get when you consider things of the form A plus BI plus CJ plus DK. So you have not just one new symbol I, like for complex numbers, but also j and k, where I, j, and k all have the complex property that their square is -1. But in addition, there's some other relations, and maybe I'll expand on Hamilton here and explain that I times j is k, and j times k is I, and k times I is j. But if you reverse the order, j times I is minus k times j is minus I, and I times k is minus j. So this is a little bit expanding on his laws, but these are the rules that allow you to multiply any two such quaternions. Okay? Okay, so more explicitly, so in more detail, here is officially how you multiply quaternions. Addition is just in the obvious way. So to add 1 plus 2i minus 3j plus 5k, if we wanted to add this one to 2 plus 0i minus j plus k, we would get 3 plus 2i minus 4j plus 6k. Just add the components in the obvious way. Multiplication is the tricky business. And here's how you multiply. So this is just a restatement of what's going on here. So a plus ib plus jc plus kd times alpha plus I beta plus j gamma plus k delta equals A alpha minus B beta minus C gamma minus D delta plus I times A beta plus B alpha plus C delta minus D gamma plus J times A gamma minus B delta plus C alpha plus D beta plus K times A delta plus B gamma minus C beta plus D alpha. Now, I've written these things on the same board here, so if I haven't made a mistake, the expressions that are appearing here are exactly the same as the expressions that are appearing here. So if we define Q of A plus IB plus JC plus KD as A squared plus B squared plus C squared plus D squared, then Euler's result is really telling us that the quadrants of the quaternion Q1 times the quadrants of the quaternion Q2 is the quadrants of the quaternion Q1 times Q2. Okay, but there's an important difference between this and complex numbers. The important difference is you can see that this is no longer commutative. This is not exactly a field, not commutative. But it is associative. All right, so it turns out that quaternions of Hamilton play an important role, have applications to rotations of three-dimensional space. So in fact, they do accomplish what Hamilton set out. They help us understanding three-dimensional space, but we have to go to this four-dimensional algebra in order to understand rotations. Now, this is another story where if you really want to learn a little bit more about that, if you look in my famous math problem 13 lecture, it's all about rotations and quaternions and the relationship between them. Right? So that's a place where you can learn about this application. But it's rather pleasant topic that's after quite a long time of neglect. So quaternions were very much in vogue in the latter part of the 19th century, partly because of Hamilton's very big influence. He was a very prominent mathematical physicist. And so his position and his followers was that quaternions help us to do physics, that all physics should be written in the language of quaternions. Okay? And then there was this, alternate view that no, we don't really need quaternions. People started realizing that you could split quaternions up, that you could rewrite quaternions and split the essential thing up into a dot product and a cross product. Okay, so Gibbs and Heaviside introduced an alternate way of thinking about things, which really came from quaternions, but they sort of separated these other things. Let me explain that by rewriting the multiplication in a slightly different way. So if I take a quaternion Q, and let me write it as, say, A plus IB plus JC plus KD. Okay. If I write that in a slightly different way and write it as a pair AV, A is that number, and V is now the vector, the three-dimensional vector, B, C, D. Then the multiplication can be written in the following way, that A1 times V1 times A2 V2 can be written as an alternate way of thinking about how you multiply quaternions as A1 A2 minus V1 dot V2, where this is the familiar dot product of two ordinary vectors in three-dimensional space. Yeah? I think pretty well, yes. I think the dot product really sort of emerged from people studying quaternions and realizing that there was a dot product in here. Of course, the idea had sort of been floating around in other ways indirectly because the dot product is such a fundamental thing. But I think sort of people really identified it as a separate issue at this point in time. So the dot product appears here, and then when we look at the vector part of this product, we get A1 V2 plus A2 V1 plus V1 cross V2. Okay. So here is the ordinary dot product of two familiar three vectors, and here is the familiar cross product that is known to all students of physics. So when we write things like this, the multiplication of quaternions, we can see that somehow it's equivalent to understanding the dot product and the cross product. And Gibbs and Heaviside came along and said, why don't we forget about quaternions and just focus on the dot product and the cross product instead? So we're just working in three-dimensional space. And there was a major controversy between these two schools of thought. And ultimately, Gibbs and Heaviside won. And that's why you, undergraduates, learn about the dot product and the cross product in first year, but you don't learn about quaternions. And that's why physicists generally frame things in terms of dot products and cross products. But it's interesting that somehow the circle has come around again, and now quaternions are more in vogue than they used to be, because people who are doing programming video game programmers and people who are engaged in situations where you have to understand rotations really well. You have to make a lot of computations with rotations. It turns out that the quaternion language is in fact more efficient for working with rotations than matrices as in linear algebra. So the quaternions have made a resurgence due to their natural usefulness for rotations. Okay, I want to talk just now finally about a variant of this. So Hamilton had a friend, John Graves, that he corresponded with quite a lot. And Graves, when he heard about quaternions, complimented Hamilton and said, this is all really great, but what about, can you go further? Can you go to, say, 8 dimensions? We're going from complex numbers, going from real numbers to complex numbers, we're multiplying by 2. Going from complex numbers to quaternions, we're again multiplying the dimension by 2. What about multiplying by 2 again and going to an 8-dimensional arithmetical system? And so Graves started working on this, and a few months later he discovered, in fact, an 8-dimensional arithmetic. And these things are called octonions. And they're usually denoted O. By the way, quaternions are usually denoted H in honor of Hamilton. Okay. So we have this sort of system, Q, C, H, O, or Q or R, if you believe in real numbers, which I don't, but okay, you no doubt think you do. All right, so in each case we're sort of multiplying by 2. And the octonion arithmetic is a little bit more complicated because it's 8-dimensional. So not only do we have an identity, we have an I, J, and K, but now we have 4 more things, L, M, N, and O. And then it turns out that the multiplication can be kind of encoded in the following diagram, pleasantly. So we put an O here, a J here, an M here, a K, an N, an I, make an L, make a circle here, and we put arrows. That way, that way, that way, that way, and this way. Okay, and this funny looking diagram, which has these 7 nodes corresponding to these 7 here, it tells you how to multiply any 2 of these things. So first of all of them square to -1. So I squared equals J squared equals all the way up to O squared equals -1. And if you want to multiply I times K, what you do is you find the line that contains I and K. Okay, there's an I and there's a K. So the line that contains I and K in this diagram is this line here. This is also a line. And that line then contains a third point, namely J. And if we're going from I and multiplying I times K, we get J but with a minus sign because we're going against the flow of the arrows. So I times K would be minus J. Or for example, J times M would be O, because along here, J times M would be O. Okay, so then there is this is an arithmetic which is no longer commutative, not commutative, and in fact it turns out to be also not associative either, as Hamilton observed. So we're losing not just commutativity, but we also lose associativity. But we do have a sum of squares identity. In other words, it is true that if you have two numbers which are the sum of 8 squares, then there's a formula that you can use to write the product as a sum of 8 squares, which is in the same spirit as Euler's formula, but has 8 squares in each term. Okay, octonions were also, in fact, independently discovered by Arthur Cayley, who was a very prolific English mathematician around that same time. And there was a bit of dispute about priority because Graves didn't get published quite as promptly as he should have. In any case, octonions have never really played as big a role in physics as the quaternions, but surprisingly, in recent decades, it's become known that octonions do have a very interesting connection with something, a big symmetry group, let's say, called E8. So there's a big symmetry group. Physicists are very interested in symmetry groups, and there's these various families of symmetry, simple Lie groups, and E8 is sort of the biggest exceptional Lie group, whatever that is. And it turns out that there is a very interesting and subtle connection between E8 and the octonions of Graves. So they're not out of the picture yet, and they still may play an interesting role in our understanding of modern particle physics, because there are people who think that E8 is important for understanding modern physics. Okay, so maybe I'll end just by saying a few words about Hamilton. Hamilton had a very interesting career. He was also rather unlucky in love, on a personal note. So he was in love twice with some beautiful women, but for some reason he couldn't get up the courage to sort of ask them to marry him, and so he was heartbroken twice in his life. And there's a sort of a famous sad kind of story. There was this one woman, I think her name is Ellen de Vries, who lived in a place called Kurnaw, and he was in love with her and wanted to marry her, but she chanced this remark, and she said at some point, well, I would never want to leave Kurnaw. And so he ended up interpreting that as a rejection, that he was, because she wasn't going to leave Kurnaw, so she could never come and live with him. So he went away heartbroken and wrote this sonnet called, something like on her saying she'd never leave Kurnaw, or something like this. Anyway, but he did end up getting married eventually, but it was perhaps not as happy a life as his success in maths and physics would indicate. All right, so that's a taste of hypercomplex numbers, and next time we'll see some more extensions of this when we talk about simple Lie groups. So see you then.